Kids, you know what's really cool? Chemistry. But do you know what's even cooler? Using that chemistry to do funny things with really interesting elements. Today, we will be taking a look at an experiment that someone did in 2008 to remove plutonium, americium, and curium out of large soil samples. Despite the age of this article, this is an interesting approach to analyze actinides in soil samples. This came out of a need to measure actinide isotopes with low detection rates for environmental monitoring. The procedure being explored in this article came from a pre-existing method using cerium fluoride to remove the soil matrix and allow actinide analysis in 5 and 10 gram samples of soil. This process also has good tracer recoveries of at least 90% and excellent removals of interferences such as polonium-210 and thorium isotopes. This new method will be looking at 100 and 200 gram samples instead. Other methods have used other materials like diphosphine resin and HEDPA extractant or calcium oxalate and iron hydroxide precipitation. But these methods either require a lot of acid rinses or a large resin column, about 4 milliliters of resin, along with having tracer recoveries that were between 40 or 70%. Alpha spectrometry was also pretty difficult too, as resolution was poor between the americium-243 tracer and americium-241 peak. This technique being explored is reported to be simple, effective, and uses smaller resin cartridges to separate the actinides from the soil samples. This procedure involves an acid leach step of the soil matrix and iron hydroxide precipitation to collect the actinides, and cerium fluoride precipitation is used to eliminate the soil matrix. This step also adjusts the valence of uranium to select against precipitation during the matrix removal, meaning that interference from uranium is minimized during analysis. There is also the use of nitric, hydrochloric, and hydrofluoric acids throughout this process. This method uses TEVA, TRU, and DGA resin cartridges that are about 2 milliliters in volume in one multi-stage column, and the separation of the actinide isotopes allow for alpha spectrometry. The DGA resin also has a strong retention for americium and curium, while also separating actinium-225 from americium and curium isotopes to eliminate interference on curium isotopes in alpha spectrometry. Plutonium-242 and americium-243 tracers were used for the soil analysis and had a reported activity of about 2 picocuries per milliliter, while laboratory control standards were analyzed using plutonium-238, americium-241, and curium-244 standards. Finally, there is a vacuum extraction of the actinides for analysis. For this experiment, it would take too much time to describe each step of the experiment, so I will summarize it the best I can. To prepare the soil samples, they first took a bunch of soil and dried it in a furnace before being taken as sample aliquots, with 100 and 200 gram samples being analyzed. After these aliquots were placed into 11 glass beakers, the tracers were added and then thrown back into the furnace for further heating. After adding nitric and hydrochloric acid, the samples were then centrifuged to get the leachate and solids, with this being filtered out and being doused in hydrochloric acid to get filtered out again. This solution was then evaporated on a hot plate, and the nitric acid was added and the soil was evaporated again. After being ashed, the solids were transferred to crucibles to be first placed on a hot plate to evaporate to dryness and then placed into a furnace. These were then taken out and placed on a hot plate. Cerium nitrate was added and then centrifuged, and the remaining solids were dissolved in hydrochloric acid. hydrogen peroxide was also added to make sure there was minimized uranium precipitation. The resin columns were then stacked with TEVA, TRU, and DGA resin columns, in that order, in a vacuum box. Sulfamic acid and ascorbic acid was added for valence adjustment, and then sodium nitrite was added to adjust the plutonium to the plutonium 4 plus ion. The sample was loaded into the columns as well. There are also many other steps involving many acids to rinse out the columns and filter out the actinides of interest, any remaining solar matrix, or other things such as rare earth metals or residual uranium. The actinides often resided on the cartridges after each process, and these actinides were stripped to be placed in glass beakers for analysis. Also, the flow rate for the column was 1 to 2 milliliters per minute, which is faster than the 0.25 milliliters per minute for gravity. Sample loading was done at 1 drop per second, with column rinses at 1 to 2 drops per second. Plutonium, americium, and curium measurements were performed by alpha particle pulse height measurement using passivated implanted planar silicone or PIPS detectors. Looking at the results, the tracer recoveries were pretty good on average, and the measurement was accurate as well. It seems that going from 100 grams to 200 grams did not have any challenges for analysis. The spectra also reportedly had good resolution. The plutonium-242 tracer recovery was about 82.1%, with the fold width half maximum being 53 keV, showing good resolution. The americium-243 tracer recovery was 97.5%, with the full width half maximum at 66 keV. This experiment also took a lot of time. The soil prep was 4 hours long for the initial step, and then 8 to 10 hours for the chemical preparation. The column work took about 4 to 5 hours for the actinides to be separated and purified, and the samples were also counted for 16 hours. The minimum detectable concentration for plutonium, americium, curium was 3 to the negative 5 picocuries per gram for a 200 gram sample counted for 16 hours as well. Until next time, I'm Fake Salmonella, and thank you for watching.